This webinar will be hosted by Anson. He's from MIT, and he will talk about Conveyal accessibility tool. So since Anson is ready, I would like you to introduce Anson and Diego, who is from WRI, and I think you guys would like to talk about the WRI Center. So are you there, Diego?
Hello, Nicolas. Hello.
Hello, Diego.
Yes, I can hear you, but you can't hear me.
Yeah, I can.
Oh, you can? Okay, thanks. So first of all, I'd like to thank the BRT Center of Excellence, who we're $I. It's a partner institution. We are want to thank them for lending us this platform where we're making possible the widespread the showcasing the accessibility analysis that Conveyal has developed in partnership with WRI and the World Bank. This goes back a couple of years, and I'm gonna pass the word briefly to Anson, who will be showcasing what they've done, the new things in accessibility, the tool, the new functionalities. And this is a tool that we've been working with for a couple, 2 years, and mainly in developing countries, putting forward new type of analysis, which is it's been a little bit more difficult in the past because of many reasons, computing power, data. But now with this new cloud computing and different resources, we've been able to really put forward new analysis. So I'll pass the word real quick to Anson, who will introduce us to the work they've been doing now.
Thanks a lot, Diego. I'm going to go ahead and start sharing my screen. And if other people would mute their microphones just so we don't get feedback. All right, so in the webinar, you should have a chat window to be able to ask questions. And let's see. If someone could go ahead and let me know that they can see the screen, that would be great. Great. So I'm going to talk this morning a little bit about Conveyal Analysis, which is a tool we have to do sketch planning for public transport. I want to thank the BRT Center for being able to host this webinar, and also to WRI for their continued engagement with this tool, and for co-hosting this webinar with us. We're really excited to be working with WRI. As Diego mentioned, accessibility indicators have been kind of recommended in urban policy for quite some time. And one obstacle has been the computation power. So I know people can see my screen. If someone would also let me know that the audio is working okay. I think some people may be having a slight echo. Okay, I think I'm getting feedback that it's okay, so I'm going to go ahead and continue. Again, if anyone does have problems, please do let us know in the webinar chat box. So just a quick overview of what I'm going to be talking through today. I'd like to start off talking briefly about locational accessibility indicators. Diego already mentioned some of that. I'll go through a little bit of the functionality of Conveyal Analysis and then get into some future research and some of the latest extensions that are being made to accessibility indicators. So locational accessibility indicators are holistic measures of the combined performance of the land use and transport system. So traditionally, transportation systems and projects have been evaluated from the point of view of travel time savings. Basically, if this project will save 10,000 people 30 seconds each, we can multiply that together, multiply it by a value of time, and come up with some sort of benefit of a project. Those traditional measures disregard what people are actually accessing. A minute saved is the same regardless of what people are trying to get to. The accessibility framework takes a slightly different view and considers not only the transport system, but also where people are trying to go. So a typical cumulative opportunity measure, for example, might be the number of jobs people could access within 45 minutes. So with an improvement to the transportation system, you may increase access for people by 10,000 jobs or 60,000 jobs or 100,000 jobs within a reasonable commute time. Those measures, these cumulative opportunity accessibility indicators, are some of the most easy to communicate. There are other more refined measures that take into account, for example, the fact that an opportunity farther away may be less valuable than an opportunity that's close by. So there can be weighting kind of in traditionally that's been done through gravity functions or other functions that take into account farther destinations are less. There's been a lot of research arguing that accessibility indicators can foster more sustainable outcomes. They can favor kind of denser urban environments rather than simply free flow speeds on highways. But many of these indicators, despite decades of academic research, have not been implemented in practice. There have been some recent papers kind of trying to explain why that might be. But part of it, like Diego has mentioned, has been computational costs, that it's relatively straightforward to run a model and come up with time savings, but then multiplying that or superimposing that on a large regional land use data set can be computationally intensive. A couple other things to mention about accessibility indicators. First, they're kind of growing in terms of policy relevance. The World Bank, I know, has been one example of groups trying to push forward an accessibility agenda. In California, some recent legislation has changed thresholds of environmental review away from typical level of service traffic indicators and delay indicators toward more accessibility-focused indicators. And there's kind of increasing recognition that these indicators are better for forming urban policy and for guiding decision-making around urban transport projects. I'd also like to share a couple of great tools that have come out just in the last couple of years in terms of online communication. So as the recognition of accessibility's relevance has grown, a number of web-based tools for communicating accessibility and helping people explore the accessibility impact of different projects have come online. One example I'd like to mention is the Accessibility Observatory at the University of Minnesota here in the US. So if you go to ao.umn.edu, you can see maps for the largest US metropolitan areas of how many jobs are reachable by auto and by transit from blocks throughout metropolitan regions in the US. Similarly, in London, Transport for London has put out a great new web mapping tool called WebCat. If you go to tfl.gov.uk/webcat, you can explore both the accessibility provided by London's existing public transport system, but also the projected future accessibility when projects like Crossrail 2 come online. You can compare the system today using all modes versus only step-free modes and stations. So for example, someone who's using a wheelchair or a stroller might have reduced access because they can't use the full system. All of this, to sum up this first part, all of this is saying that locational accessibility indicators try to holistically integrate not just the transport system, but also urban land use, the opportunities and destinations to which people are trying to travel, and individual constraints such as needing step-free access. Before I go on, I want to pause here. If there are any questions, please do feel free to type them into the chat window. I'm keeping an eye on that, so if there are questions that come up during the webinar, I'll try to answer. We'll also leave plenty of time at the end for questions. So moving on now, talking a little bit more about our approach at Conveyal to accessibility. One thing we do is take a probabilistic approach to measuring accessibility. This is especially important for public transport. Travel times by public transport are subject to both variation and, in sketch planning, they're subject potentially to quite a bit of uncertainty. When we talk about variation at Conveyal, we talk about variation due to departure time. If I walk out my door and wait for the bus and I just miss the bus, I may have to wait quite a long time. My level of access to opportunities may be reduced. Versus if I walk out my door and immediately make the bus and have ideal transfer, minimum transfer time, that may correspond to kind of a maximal level of accessibility. So depending on when exactly I leave, there can be significant variation in accessibility. When doing sketch planning of future scenarios, oftentimes scenarios are only represented in terms of rough frequency-based lines or routes. So we know that a new line may run every 10 minutes or every 2 minutes, but we don't know the exact timetable at which that line may run. It's a little bit too detailed to get into at the sketch planning level. Depending on timed transfers, phasing, this could lead to variation or uncertainty in accessibility. For example, if there are many routes sharing one corridor, if those routes happen to be evenly spaced so that passengers experience lower wait times, specific timetables could lead to higher levels of accessibility. Whereas if those timetables are not well phased, people may need to wait multiple trips. Buses may be bunched, for example, and so that could lead to lower levels of accessibility. To account for this, we actually calculate complete journey travel times for every possible departure minute over a specified window. So the example on the right here is looking at, from this origin location, the travel time between, the median travel time between 5 p.m. and 6 p.m. in Greater London. So this bar is showing the travel time cutoff increasing from 15 minutes up to an hour and 15 minutes. And on the right, you can see blue isochrones extending out as that travel time cutoff increases. So within 30 minutes, you can get to most of central London. Within an hour and 15 minutes, you're getting out into many of the suburbs on, for example, National Rail Service. As I mentioned, this is a complete journey travel time, so it's taking into account walking to an origin station from this exact origin, any waiting time, in-vehicle travel time, transfer time, and egress time to get to any of these destinations. This is being calculated on a 200-meter, approximately square grid. So this can take into account, this helps address the modifiable aerial unit problem. Basically, we're using a regular raster grid. This lets us be a little bit more precise than typical traffic analysis zones, maybe much larger, and which may kind of obscure important walking or biking access and egress legs from transit. As I mentioned, this is calculating travel times at every minute from 5 p.m. to 6 p.m. And what you're seeing in this cumulative distribution on the left of the figure is an envelope around the median travel time within that window. So the lower edge here, the lower edge of this envelope, is the minimal accessibility, or kind of the basically the lowest level of access if I were to leave between 5 and 6 p.m. So say if I walk out the door at 5:20, I've just missed buses and trains and will need to wait the maximum amount of time. This bottom would, for example, at 45 minutes, I would only be able to get to 2 million jobs. The top of the envelope corresponds to the accessibility with the best travel time. So if I am able to choose my departure time and leave at exactly the right time, then within that same 45 minutes, I would have access to maybe 3 million jobs. I mentioned the modifiable aerial unit problem. I see a question here. Part of this is that we can actually specify the resolution of the grid cells and their offset. So if I wanted to test the impact of different grid cell sizes, different kind of starting and ending points of those grid cells, I could do that. And again, this helps move away from kind of larger aggregate zones that are often used in accessibility analysis. The last thing I'll say here is that to take into account the fact that explicit timetables may not be specified, for frequency-based lines, we actually run a Monte Carlo simulation to try out different potential timetables that would meet frequency requirements. And I can say more about that at the end if there are more detailed questions. So a little bit more about kind of the computational setup we're using here. All of what we do at Conveyal is open source software. So people are free to kind of download, install, and use our software however they want to. The specific analysis platform that I'm showing, so I should mention we have other tools for GTFS creation, management, etc. The tools I'm showing here are basically relying on 3 software packages. The bottom one is our multimodal routing engine called R5. So if you want to check out the source code for that on GitHub, it's at github.com/conveyal/R5. The cloud-based kind of cluster computing setup we use is Analysis Backend. And then the web interface I'll be showing is Analysis UI. So that's a browser-based interface for scenario editing and evaluation. In terms of the input data required for these accessibility analyses, basically we load up a baseline transit network in the GTFS format. We load up the transit network and schedules. We load for the pedestrian and street network OpenStreetMap data. And then for the opportunities to which people are trying to read, to which people are trying to travel, we can load up any arbitrary shapefile. So I'll show some examples of those in a little bit. In the case of the United States, we actually automatically download a block level data set provided by the Census Bureau, the LEHD Longitudinal Employer Household Dynamic Survey. And that gives us block level data on residents, workers and employment. In terms of what's actually happening with the computation, in the browser-based interface, we are sending modifications on to the transit network. So for example, we may load in a baseline GTFS network, but then need to remove some trips, change the frequency of some trips, add some trips, reroute some trips. All of those can be specified in the front-end interface, and they're then sent as modifications to the server. The server will then send some of those modifications as well as routing requests. So, for example, in the past slide, I showed specific origin, specific routing options in terms of a departure time, window, different modes to use. So all of that's sent to our multimodal routing engine, which then returns the travel times from that selected origin to all potential destinations. The server does a bit of processing and sends back those travel time results, which can then be visualized in the browser. I should mention that this happens, at least in our hosted setup, on Amazon Web Services to take advantage of parallel cloud computing. So if needed, if we're doing a large calculation, we can actually spin up 100 or 200 of these multimodal routing workers and get results kind of through parallel processing very quickly. These tools have been extended because they use open data and documented APIs. They've been extended to kind of other front-end visualization tools that can communicate accessibility concepts to wider audiences. One project that I worked on as a graduate student at MIT was called Coaxis, and this basically interfaced with the Conveyal server and provided people the chance to try out their own modifications and see the results for public participation. So I'll mention a little bit more about that Coaxis project now, but before I do, I also wanted to say we are committed at Conveyal, like I said, to open source software, and by the end of, while it's possible to kind of run all of this software, to download it all, configure it all on, for example, your own laptop, this is what I did as a graduate student. We're committed to making that process a little bit easier and a little bit lower of a barrier to configuration. Right now, there are, like I said, 3 different repositories that need to be cloned and some configurations that need to be set. By the end of 2018, we're hoping to make this an even more streamlined and better documented process. And we're glad that the World Bank and WRI are partnering with us to help make that happen. So while it's possible to do now, it'll be much easier by the end of next year. I mentioned the Coaxis project, which was done at MIT. It's continuing at MIT, and this is basically a touchscreen tool for communicating some of these same accessibility concepts in kind of public engagement or stakeholder engagement settings. So there have been a couple of publications that can come out of this. What I'm showing now is an example that we tried in London, thanks to a partnership with Transport for London. Again, this was when I was still a graduate student at MIT. And this was letting members of the public play around with an open source mapping tool on this touch screen, test out the impact of different closures, different scenarios, and help them kind of understand some of those impacts from the point of view of accessibility. I want to pause one more time for questions if anyone has any questions on what I've mentioned so far. All right, so looks like we have one question coming in. I'll go ahead and let this video finish up. And so one of the question we have here is that one of the inputs for the road network is OpenStreetMap data. And have we had issues using OpenStreetMap or OSM data in cities that are not well mapped? So we have tested out how this works in cities where OpenStreetMap coverage may not be as good. You may have heard of the Digital Matatus project that looked at creating a GTFS for the semi-formal and informal system in Nairobi. We loaded in those GTFS data, but actually it looked like some of the OpenStreetMap network was not as dense, or it was somewhat sparse or lacking in the Nairobi area. And we did see some kind of holes in the resulting isochrones. So again, this is reliant on the input data. That being said, there have been a number of mapathon projects and other projects to help get more OSM coverage in different locations. So yes, it is reliant on whatever data are being input. We'll go ahead and move on now briefly to talk about how we edit scenarios. So like I mentioned, a baseline OpenStreetMap network and GTFS transit network are loaded into Conveyal Analysis. But one of the benefits of this is being able to make modifications to that network. So here I'm showing an example in Los Angeles of the Orange Line bus rapid transit corridor. And there's been a proposal to add some overpasses to this BRT corridor to reduce grade separation issue, or to help lead to grade separation and increase speed. So this is showing briefly how I would choose a segment of that corridor and then scale up the speed by 40%. So you can see that that kind of modification is very quick to make in the interface. I've chosen a route, chosen a segment of that route, and say scale the speed by a factor of 1.4. Here's a different kind of modification. In this case, we, oops, this is repeating the same one. Let me move ahead. In this case, we're going to be extending a line or rerouting a line. So Metro in Los Angeles is currently building the Purple Line extension, which will extend a heavy rail service from its current terminus at Western Avenue out toward an area of Los Angeles called Westwood. So you can see I'm using the browser here to extend the route. I'm adding stops for this service at existing stops. So you can see those blue icons there. If I want to add a stop at a new location where there's not currently a stop, you can see I can add one there. It shows up in black. I can change the alignment, drag and drop the route. And then from here, I'll want to specify a speed for this new route, so maybe 60 kilometers per hour, being ambitious, and potentially dwell times at each of the stations. I can then go ahead and add a frequency to specify how often this trip runs. So I'll show an example of that. Or sorry, in this case, this is rerouting an existing route. So it will, by default, use the existing frequency for this trip pattern for the trips that currently run from Union Station to Wilshire and Western, and it will just extend those trips. If I wanted to modify the frequency of those trips or modify the frequency of a different set of trips, I'll show how to do that in a minute. Here's an example first of adding a new route that actually follows the streets. So this could be adding a bus shuttle service. You can see I have follow streets checked. That'll make it follow the streets. I can set a default stop spacing to automatically add stops. I can add frequency for different time windows, change the speed of this new bus route, and then I could kind of edit any of these stops. I could turn them into control points that kind of set the alignment. I could add or remove stops to that. So I did mention changing. So I'll show one more case of adding a new line. In this case, I might be adding a new subway service. So not just extending a service, but adding a completely new one. And in this case, let's be super ambitious and say that under the Sepulveda Pass here, this new rail line will actually run maybe up to 80 kilometers per hour. So I could kind of go back, set my stations, set up the alignment. And then once I have this set, I can add, like I said, a weekday timetable, a weekend timetable, maybe run every 4 minutes during the weekdays, and maybe only every 6 or 8 minutes during the weekends. But like I said, I can actually modify the speeds of different segments. So if I want to, in this case, run much more quickly through the tunnel where there are no stops, I could edit just that segment. And then, like I said, go back, change different timetables. So there are lots of very detailed, specific modifications I can make. Adding new services, removing services, adding stops, removing stops. The last example I'll show here is, like I mentioned earlier, adjusting the frequency of an existing service. Oh, I guess that one didn't make it in here. But yeah, that would be kind of selecting a service and saying, okay, how frequently do I want this to run in different timetables? So that's all kind of editing scenarios. Now I want to talk briefly about kind of getting a feedback loop, about evaluating those scenarios. So one of the things we've observed in how people use scenario planning tools is that there's often kind of a barrier to usage. The turnaround time can be a little bit long between actually formulating and editing scenarios and then seeing their impacts. One of our goals with Conveyal Analysis is to really reduce that turnaround time so that there can be rapid generation, exploration, evaluation of scenarios. And then that turns into an iterative process to kind of test out different options. So what I'm showing now is how we evaluate some of the scenarios I just put in. So I've made this pink line run more frequently. I've added in this blue line, the purple line extension, and I've made the BRT corridor run more quickly. You can see that as I'm dragging this destination marker, I'm seeing two box plots, which represent the travel times in the two different scenarios. In the baseline scenario, which is basically my baseline OpenStreetMap and GTFS data without any modifications applied, and then the modifications I've added. So I'm looking at travel times now, the distribution of travel times between, in this case, 7 a.m. to 9 a.m. from this origin location to this destination location. So in red is the baseline case. If I time my departure from this origin and I choose the exact best departure time between 7 a.m. and 9 a.m., I can make this trip in as little as, it looks like, 35 minutes here. Worst case, if I just miss that trip, if I just miss that and I choose kind of the worst possible departure time, it can take up to 95 minutes. The median travel time is about 70 minutes. That's again in the baseline case. In the case of the upgrades I've applied, so making this pink line run at 4 trains per hour, that's a Pacific Surfliner for those of you that know Los Angeles, upgrading this BRT line, adding in these lines here, the variability in my travel time is significantly reduced. Basically, because those lines are running more frequently, even in the worst case, I'm only having a total door-to-door travel time of about 60 minutes. And best case, my travel time's reduced and the median's reduced. So again, you can see how that travel time, that distribution of potential travel times changes for different origins. I can then kind of take a composite view of that and see for a given origin, how long does it take me to get to all potential destinations? So within a given travel time cutoff. So this is comparing, again, two isochrones, one for the baseline case and one for the case with the upgrades, saying how far can I get in 45 minutes from this origin? So in red, you can see I can barely get down to Boulevard here. I can get out maybe to Burbank and up to San Fernando. In blue, with the new extension turned on, I can get down here, transfer onto my new line, and get all along it, and get up into San Fernando. And basically, I have an increased reach or increased access because of the modifications applied to my transit scenario. Each of these dots represents a cluster of jobs. Like I mentioned, for the case of the United States, we automatically download block level employment data. So you can see there are job clusters throughout the region here. And this cumulative plot is showing the number of those jobs I can reach within any travel time cutoff. So from this specific origin, within 30 minutes in the baseline case, I could access this number of jobs, and again, there's variation around that. With the upgrades, I could access this number of jobs. Within 45 minutes in the baseline case, I'm looking at a median level of access of 253,000 jobs within reach. And with the upgrades, I'm looking at 695,000 jobs within reach. So there's a pretty major, there's a pretty substantial increase in the number of jobs reachable within that travel from this origin, given these scenarios. One of the features we have in Conveyal Analysis is the ability to repeat this calculation for every potential origin in the region. So not just choosing one specific origin, but actually saying, what will the difference be between those two scenarios for every origin in the region? Here you're seeing a comparative view, basically saying the additional jobs reachable given those upgrades. So in darkest red are the areas that have up to 1,077,000 additional jobs reachable within, in this case, 1 hour. You can see that as expected, there are kind of increases along the new lines I put in. The areas in this kind of light blue shade have between 56 and 164,000 additional jobs reachable, given the upgrades. And surprisingly, there are actually areas that aren't proximate to my new upgrades, but that see an increase in the number of jobs reachable because of network. Transportation is a network, and so if I'm applying an extension here and a new line here and speed upgrades here, because of the fact that I can transfer onto those services from different lines in different parts of the region, I'm actually getting increases in accessibility in other parts of the region. This could be one of the key sets of insights available through a tool like Conveyal Analysis, being able to see where in the network changes may happen, even though the actual construction and the actual upgrades are taking place in different parts of the network. So before I move on, there was a question on the previous section. Is there a way to upload user input road network data? The answer is yes. We do offer the option to upload your basically custom OpenStreetMap data. So for example, if you wanted to try out a new highway network and you didn't want to make those changes to OpenStreetMap.org because it reflects some kind of future state that shouldn't yet be represented in OpenStreetMap, you could download the existing OpenStreetMap network, use a set of tools such as JOSM or other OpenStreetMap editing tools to just save kind of a local version of that new network, and then upload it here. So you could see, for example, in this case, I was comparing two different transit scenarios, but we could actually compare two different road network scenarios. We could also keep the transportation network the same and upload two different shapefiles. We could try out different land use scenarios. So say, for example, let's keep the transit network the same, but have one set of destinations representing jobs today, and one set of destinations representing the distribution of jobs that we forecast 10 years from now, and see how people's access to jobs may increase given changes in land use. So I've talked mostly about editing transport scenarios, but this same tool and the same framework can be used to test out different land use scenarios as well. So I mentioned loading up different shapefiles. Now I'm showing an example in Mexico City. This is the number of jobs reachable from this example origin in Mexico City. You can see here I'm doing a comparison between the baseline, which only includes the formal GTFS, the GTFS network for the formal network, and then a series of modifications that I've loaded in from a shapefile representing the alignments of informal transport service. So I can upload data as GTFS, as I mentioned, but also if I don't have a well-specified GTFS, I can upload just a shapefile representing the alignments of different service and add in assumptions about that. With just the formal network, you can look at 2,036,000 jobs within reach. Adding in the formal network, that expands it to 2,043,000 jobs. So that's looking at access to jobs. From this same location, I could also look at access to potential workers or access to population. So I've changed the destination I'm looking at. Instead of dots representing jobs, now the black dots showing up on this map are representing population clusters. So you can see kind of the population density within the region. And then another example, if we have land use on healthcare centers, for example, this is looking at the number of health centers within reach. So you can see dots here representing the locations of health centers. And from this location, maybe the 75-minute stop is too high. Maybe I want to know access within 30 minutes. And you can say maybe about 25 jobs would be 25 health centers would be within reach in a 30-minute cutoff. Just to review, land use data or opportunity data sets can be uploaded as aerial shapefiles, as polygons. They can also be uploaded as point shapefiles, point layers. So that's a little bit about how to evaluate different scenarios. I would like to leave plenty of time for questions, so I'm going to go through the final two sections fairly quickly. These are representing, these are getting a little bit more into some future research, some extensions we're building into Conveyal Analysis. The first is looking at different employment. So here's an example analysis we did in London. And you can see the darkest blue shades here represent areas. Now we're looking at firms' access to employees. You can see that the darkest areas have access to upwards of 1.8 million employees in Greater London. But it's important to consider how the distribution of access might vary between different locations. So here we've just limited our analysis to the formal boundaries of the Greater London Authority. And now this histogram is showing the distribution of access to workers. So you can see that there are some employment locations that have access to a relatively low number of workers. For example, this peak here is around 200,000 workers within reach. And there are about 600,000 firms kind of within this, or 600,000 jobs that have that level of access to potential workers. There's also a second peak that happens here at a level of access of about 1.5 or 1.6 million workers within reach. So you can see here kind of the bimodal distribution of access. There are firms in central London that have a very high level of access, and then there are firms in outlying areas that have a lower level of access to workers. The median level of access to workers within Greater London is having 712,753 workers within a 45-minute commute. But that median, as you can see, falls kind of in the middle of this distribution, and reporting only the median level of access might obscure the fact that you actually have a pretty important bimodal distribution here. That bimodal distribution can actually be decomposed by different industry types. So if we break down accessibility to workforce by firm type, you can see that manufacturing firms, for example, would tend to follow that left peak distribution. And finance firms, which tend to be more centrally located, would follow kind of the part of the distribution that peaks on the right. This is all to say that having the ability to rapidly test different land uses and different transport scenarios lets you understand kind of the breakdown of access or accessibility in a metropolitan region. I'm going to go ahead and skip this slide, but it basically looks at matching between worker type and job type, and says that for some industries, the joint firm and residential location confers an accessibility advantage. So IT workers and finance workers in London tend to be well located, and their jobs tend to be well located, whereas other types of industries don't experience that advantage. The last thing I'll mention is kind of extensions to look at reliability in terms of transit operations. Everything I've shown so far assumes that public transport operates as it's scheduled. And depending on the system, that can be a pretty strong assumption. There have been a number of recent papers looking at how to incorporate unreliability in actual operations into accessibility indicators. So accessibility-based indicators of reliability. For the case of the road network, a recent paper at the University of Minnesota looked at kind of these rings of unreliability in the Minneapolis-St. Paul region. So if you look at basically the median speeds on the roadway network, calculate accessibility that way, and then compare that to accessibility calculated using 10th percentile speeds, you could see a difference in the level of accessibility. And that difference would represent kind of the cost of congestion, in a sense. You could do the same thing looking at the difference between the 10th and the 90th percentile speeds. And you can see here kind of the darkest red areas are where the 20-minute accessibility by auto has the biggest difference between the congested and the uncongested network. In terms of transit, a recent paper looked at the Toronto case and archived transit vehicle locations and compared the real accessibility versus the scheduled accessibility. You can see here in dark red are the areas where there was a greater than 25% difference in the actual accessibility by transit versus scheduled. We can look at some of these same concepts in Conveyal analysis. So in this example, the red is again showing the baseline case of scheduled transit service, the 45-minute accessibility from this origin location in Boston. The blue is showing the actual accessibility based on 10 weekdays worth of AVL data, of our automatic vehicle location data, between 5 p.m. and 6 p.m. You can see there are some areas that even though the schedule promised you could get from Copley Square to Dorchester, for example, even though the schedule promised you could get that far within 45 minutes, on none of the actual days could you get there. In terms of accessibility, you can see here the impact of what that does in terms of, in this case, workers within reach from that origin. So the promised level of access is about 400,000 workers within reach, but there's significant variation around that. And you can see that with this box plot, that the median is generally much lower than the scheduled level of access. And on one particularly bad day, even choosing your best possible departure time in that window would give you worse than the worst case, or even choosing the best possible departure would give you worse accessibility than the median or even the best case or worst case for the scheduled network. So again, we can do a comparison here and say in darkest red are the areas that have the biggest decrease in number of jobs based comparing actual and scheduled. So I'll go ahead and stop there. I want to leave plenty of time for questions. Please feel free to type your questions into the chat window, and I'll do my best to answer them. Thanks again to WRI and the BRT Center of Excellence for helping to sponsor this webinar. And we really look forward to having more people learning about these tools, trying these tools out, and hopefully kind of helping us to think about the next steps for applying accessibility analysis in places around the world. So I saw one question being typed. Let's see, a couple other things. So do you consider the competition for jobs in accessibility? For example, increasing accessibility in general can be bad for some workers now that more workers can compete for a position. This is a really good question. There are a number of papers over the last few decades that have looked at competition-adjusted access to jobs. So for example, if I can reach one job, but 500,000 other people can reach that same job, I need to compete for that in a way that's different than having access to a job that maybe only 10 other people have access to. We don't have a way to do that automatically yet in the web-based interface, but it is an extension we're hoping to build in the near term. You can see we have the ability to do that kind of calculation. You need to do two things. You need to say first, for each job, how many residents have access to that job, and then do a second round of calculations saying for each resident, how many of those competition adjusted or weighted jobs do I have access to? So it's a two-step process. Currently, we're doing the two steps separately. And you could, for example, do those two steps, then download the data and kind of do the competition adjustment offline. I should mention that all of what we've shown here has kind of export functionality. So you can download shapefiles representing this output here, in this case, it would be a raster grid, a GeoTIFF. And the single point analyses I was showing, you can download GeoJSON to show kind of those isochrones. But yes, currently you could do those two separate analyses, download the results, and do the computation offline. In the future, we would like the ability to do this automatically in the web interface, be able to say, run that two-step process and give me the competition-adjusted access controls. Thanks a lot for that great question. I'm watching for any further questions, and I don't see any coming in yet. If you have questions that come up at any point in the future, please do reach out to us. You can tweet at us. We're at Conveyal. Our contact information is also on our website, conveyal.com. And if you want to see more about the specific features of the Conveyal Analysis platform that I've talked about, you can see that at conveyal.com/analysis. As I mentioned at the beginning, we have a number of other tools for GTFS management, deployment. We also at Conveyal do a lot of work on strategic trip planning. So customer-facing multimodal trip planners that take into account, for example, not just walking to transit, but also biking to transit using real-time availability of shared bike systems to do trip planning on bike share to transit trips. The multimodal aspect of this is something that's really important. Additional research we'd like to do would also be extending some of these analyses to compare, for example, pedestrian accessibility or accessibility by walking in transit to accessibility by biking in transit. We do have about 5 minutes left, and it doesn't look like we have any other questions coming in. So again, if you do have further questions that come up, please do let us know either via Twitter or by reaching out using the contact information on our website. Diego, I don't know if you wanted to say any additional words on future plans for this from the WRI perspective.
Well, thanks, Anson. Really good. Can you hear me? Yeah, I think they can hear me. So really, yeah, thanks. Really good expositions you did about the tool, showcasing all the functionalities. Really, thank you. And from our side, we're thinking about engaging with cities. Basically, we're talking with cities in Mexico, Brazil, India, to see how we can use it. There's other challenges there in these cities. Basically, it's the data, the transit data. Sometimes it's in shapefile alignments, sometimes not all in GTFS, but we're making our best. So if you are interested in working, using the tool, looking at the different functionalities or things that can be done for your city in these countries, please reach out to us. I'll actually type in my email so that you have it, because it was not there. But yeah, so we're planning on working, with Conveyal, with the World Bank, extending this to developing cities where just the main need in terms of data and this type of analysis. So thanks, everybody. I think if we have no further questions, there's a question about safety. Lua.
Go ahead and answer that. Does it consider safety and accessibility? We have developed a few other tools that look at level of traffic stress for bicycling, for example. So you could say, what's the level of access using only protected bike infrastructure versus what's the level of access using, all roadways if someone's willing to put up with unsafe bicycling conditions. We are looking in a couple other projects at adding in some pedestrian safety limits. So there would be a way to consider safety and accessibility. I think that the question was, does it consider safety and accessibility? If that didn't answer the question, let me know. I should also mention that at Conveyal, we do offer consulting services using this tool. An example that we like to talk about is we actually run analyses like this at the level of the entire Netherlands. So There was a project looking at a new rail tunnel between Amsterdam and Schiphol Airport. We actually programmed in a lot of different scenarios, looking at that, looking at kind of the entire Dutch transport network. And we're able to actually affect some decision making, saying, okay, extending local service versus express service, given this new infrastructure, could actually give us different impacts in terms of accessibility. So this tool is being used in places around the world to help inform decision making around transport. All right, well, I think we've answered all the questions. Again, feel free to reach out if you have any further ones. Thank you very much for joining, for your interest, and we'll hope to...
Okay, thanks, Anson, and thanks everybody to join us on this webinar. So this was a very interesting presentation, and if there are no other questions, I think that's everything for today. I hope you can join us in further webinars, and if you're interested to perform or you have any recommendation, please let us know. So if that's all, we can give an internet applause to Anson and Diego, and we thanks WRI and VRT for hosting this webinar. So, is there a question from Manuel? I will wait. He finished typing. So, okay, he's thanking Anson.
Thanks again, everyone, and thanks again to the VRT Center for hosting.
Okay, guys, I hope you have a great week.